We will today discuss the mole, consider the mole and Avogadro's number. Now mole has the same concept. Mole has the same concept as the dozen has. For example, if I say 1 dozen of banana, 1 dozen of bananas means 12 bananas. Bananas. Similar is the case when I say 1 dozen of oranges means 12 oranges. Now this 12 is a fixed number, and this 12 means 1 dozen. So 12 is a fixed number, and of course because it's 1 dozen, but the masses will be different. 1 dozen of banana and 1 dozen of oranges, mass will be different even for 12 like objects, and even for the single one banana, mass of single banana and mass of single orange will not generally be same. That's the case for the mole and Avogadro's number. Similarly, we first how we define mole. Mole is defined as it is the amount of substance. It is the amount of substance which contains as many entities. These entities can be particles, molecules, atoms, etc. etc. It can consist ions also, but contain as many entities as there are atoms in 0.012 kg of carbon 12. This is one of the isotope of the carbon. Another isotope of carbon, you know, is carbon 14. So we are taking just the carbon 12 as a standard, and we are taking 0.012 kg of carbon, or 12 gram of carbon are taken. Carbon 12 are taken, and its number of atoms are counted, and that is a fixed quantity. We take that as a standard for 1 mole. As the 12 is standard for 1 dozen, the atoms in 0.012 kg of carbon 12 taken as a standard, and that standard is known as Avogadro's number. And Avogadro's number is defined as, we say, it is the number of atoms in 0.012 kg of carbon 12. It's the number of atoms in 0.012 kg of carbon 12. So, and it is denoted by Na or A naught, and it is 6.02 into 10 power 23. Its unit is per mole. So, now any quantity, any amount which will contain this numbers, like quantities of this number will be 1 mole. For example, if I say 1 mole of markers, these markers, then I will have to take 6.02, the huge number, 6.02 into 10 power 23 markers to constitute 1 mole. Similar is the case, for example, if I am taking water, 6.02 into 10 power 23 water molecules will form 1 mole of water. Now, roughly speaking, any molar mass, molecular mass or atomic mass expressed in grams is 1 mole. So I will say it is because H2O means 2 plus 6 is 18. If I take 18 grams of water, then it becomes 1 mole of water, or 6.02 into 10 power 23 water molecules. Similar is the case if I take 6.02 into 10 power 23 hydrogen gas molecules, then it constitutes 1 mole of hydrogen gas, and it weighs 2 grams of hydrogen, or 2 grams of hydrogen. If 2 grams of hydrogen gas is taken, it's equal to 1 mole, and it will consist 6.02 into 10 power 23 molecules of hydrogen gas. Now these are the molecules of water, these are the molecules, but the quantity is same, as in the dozen, the quantity was same. So that's the Avogadro's number, and that determines the mole. And how we do calculations with the mole, we take if you notations here, the first notation is m. M is used for any given mass, or it is also used, because notations are still to be studied, right? It is also used for mass of a single atom, or single molecule, and M capital is molar mass, N small is number of moles, N capital is number of atoms or number of molecules, Na is Avogadro's number, now this has SI unit kilogram, this has SI unit kilogram per mole. Please remember this, N capital molar mass is a unit kilogram per mole. N is number of moles, it has SI unit mole. Number of atoms and molecules has no unit. Then N Avogadro's number, it has a unit per mole. Now the first equation is N small is M upon capital M. Here N small is number of moles, this M small, this one is any given mass, and this M capital is for molar mass. Similarly, we have another equation which says N is N upon Na. N is number of moles here, this N is number of atoms or molecules, N is Avogadro's number. Combining these both equations, it becomes M upon capital M is equal to N upon Na. Now another equation which is most important, that is we write that is small mass M is equal to capital mass capital M upon Na. This is the actually this is the M small is mass of a single molecular atom. Mass of a single molecular atom, M capital is molar mass, and Na is Avogadro's number. So I always say, I always emphasize this equation because this will be used very much extensively in ideal gas equations chapter. Small m or mass of a single molecule is always found by molar mass divided by Avogadro's number. Sometimes this formula also, and this moles concept, is used to find the diameter of a single molecule or the spacing between two consecutive molecules. For example, if these are two molecules spherical in shape, we suppose they are spherical in shape, but for estimating purpose, we'll be supposing them just like the cubes. There is a justification because molecules are very small. Whether you consider them a cube or whether you consider them a sphere doesn't matter. So for all estimating purpose, we can calculate them, we can regard them as a spheres, but cubes, although they are spheres. But see this one, these are similar, this one radius r, and this is also radius r. But this becomes now, this is the diameter t. And also it is the spacing between two consecutive molecules, spacing between two consecutive molecules. The spacing between two consecutive molecules, this one is spacing between two, so spacing between two consecutive molecules and diameter of a single molecule is always the same thing. Now how it is determined? It is determined just by taking the cube root of volume of single molecule. Volume of single molecule. And how volume of single molecule is found? First, mass of a single molecule is found by formula M is equal to M upon Na. M is the molar mass, N is Avogadro's number. Now the concept of density is used. Density of one molecule or density of 1000 molecules is same. So density is mass upon volume of single molecule, mass of single molecule upon volume of single molecule. Density is still the formula for density still holds. Density of this formula is still valid, and we can say rho is equal to M upon V, or I will say V is equal to M upon rho, and we can find the V. By finding V, I can find the diameter by this one. Or I can say suppose D is equal to cube root of V, and it is cube root of V is m upon rho, and m is this m upon na, so it will be cube root of m capital upon rho and a. So density can also be found by the diameter of a single molecule, or spacing can also be found by the formula D is equal to cube root of molar mass divided by density into Avogadro's number. This formula can also be used directly.